Thank you. My pleasure to be here and be with you. And so you can see the talk has the title of Electrochemical Pathways Towards Profitable Sustainability. Um, so I'm going to begin by saying that we know that the sustainable future will be a carbon-free electric future. And that means that we have to electrify almost everything. And that means radical innovation in risk-averse sectors. So this is going to be resource intensive, and it's going to involve mining and smelting. And these are topics that people don't want to talk about. If you go to the university or the national laboratories, mining and smelting, they think of this as 19th century technology. They don't. It's not au courant. It's not nano, it's not AI, but this is where our modern world comes from. And when you look at the 21st century regulations on water and emissions, I mean, it's going to be really hard to fully electrify. And but this is where I chose to work. And I want people to understand that this is we call tough tech. It's not like writing code. You write code, we form a company, within a year, we're listed and everything's beautiful. But in this we're talking 20-year timeline, and nobody's got the patience for a 20-year timeline. So I'm going to give you two vignettes today. One of them is about decarbonization of manufacturing, and that's going to be green steel making, which is the molten oxide electrolysis, inert anode, and led to the formation of Boston metal. And then the second one I'm going to talk about is treating the intermittency of renewables. And that means massive stationary storage. And that's my invention of liquid metal battery, which then led to the formation of the company called Ambry. So let's go to the steel. If you take a look at the tonnage we're talking about, this is 2023. The 2024 data have not been tabulated yet, but 2023, 1.892 billion tons, 1.892 million tons of steel, and that led to 3.61 gigatons of CO2, and that's 9.7% of total CO2, and that's not 9.7% of what came out of the manufacturing sector. That's 9.7% of total CO2 in the world. If steel were a country, it would be the third largest polluter of CO2. Number one is China, number two is USA, and number three would be Republic of Steel, if you took all the steel companies in the world and declared them to be a country. So how did I invent beyond the blast furnace? So you know that iron is found in nature as the oxide, either hematite or magnetite. And so that's the starting point. I know that the electron can be a sustainable reducing agent instead of carbon. So when I was teaching my big freshman chemistry class at MIT, when he talked about solubility, we said like dissolves like. And so if you have an oxide as a feedstock, then why not have an oxide as a solvent? Nobody thought about this. I mean, aluminum is made, or aluminium is made by dissolving aluminium oxide in a fluoride. But I didn't want to work with the fluoride. You have to go to such high temperature to make liquid iron that I said, no, we'll go to oxide. So you can see like dissolves like. And then if it's going to be an electrolytic process, to use the electron. That's the only way you can exploit the electron. So the molten oxide electrolysis is really an extreme form of molten salt electrolysis, which is how we make aluminium, magnesium, and some other alkali metals. But in this case, with an inert anode, we would make oxygen as the byproduct, and that would be disruption. And so this is a cross-section of a notional cell. So you can see anode at the top, on which gas evolves, and you can see liquid iron at the bottom. And in between this orange zone is the molten oxide electrolyte. And so we pass current from the anode through the electrolyte to the cathode. And that electric current decomposes iron oxide. And this is where we feed the iron. It could be magnetite, could be hematite. And by the action of electric current, iron becomes liquid iron on the floor, and oxygen evolves on the anode and bubbles away. So that was the concept behind it. And this would have a lower capital cost than a blast furnace per ton. I mean, blast furnace, you're talking about 2 million tons is probably $5 billion, but you could be economically viable with this molten oxide technology at, say, 100,000 tons. So that means that your barrier to entry is much lower. And why it's so cheap is we don't have coke ovens because we're not using carbon. We don't have a cinder plant. Cinder is to take the iron oxide and make it into porous pellets. But here we just feed the iron oxide into the molten oxide. So it doesn't matter if it's big chunks, if it's small fines, it all dissolves anyways. And we don't need a basic oxygen furnace. This makes pure iron. It's not like in the blast furnace where you end up with pig iron and it has very high levels of carbon. And so, as I said, this makes it scalable at much lower tonnage. So this is some work I was doing in the basement of building 4 at MIT. This is about 15 centimeters across. And this is an alumina tube. And you can see at the top a fixture here with electrodes and thermocouple, various leads coming out. And down here, just in the dark area at the bottom, is where the molybdenum disilicide windings are. And it's glowing there at about 1600 degrees Celsius. And some of that light is radiating up the aluminum oxide tube. And this is the early experiment. So as I said, we're running about 1600 centigrade. And this is actually showing you, we have a viewing port on the top of that cell. So we're looking down. This electrode I've labeled plus, this is the anode. And at the time, we were funded by NASA. NASA was interested in making oxygen on the moon. And so this is similar in composition to the lunar regolith. And I'm going to start the video. You will see oxygen bubbles forming on this anode over here. And this other electrode, that's a molybdenum plate, and it's vertically disposed. Maybe you can see the very faint outline of the top of the molybdenum plate. It's vertically disposed. And so liquid iron is forming on the surface of that plate and falling to the bottom. And so you can now see that so it's a silicate melt. It's iron oxide dissolved in silica, alumina, magnesia. And so it's viscous, but it still allows for adequate mass transfer. You can see bubbles coming off and so on. So that was very early work. And as I said, this was funded by NASA. They wanted to go to the moon at one point. All right. Now, we knew that if we were going to use platinum group metal as the anode, that would never make it in industry on planet Earth. And around about 2011 or so, came in my lab the discovery of a practical inert anode. And the practical inert anode was an alloy of chromium, 90% chromium, 10% iron. And this forms a surface film that's protective. And I'll show you some images. This is some early work that we did. In the left frame here, you see the machined anode before it's immersed in the electrolyte. And then this is after 2.5 hours at 1565 degrees Celsius. The reason it looks so ugly is that it's covered with drag out of the electrolyte. The actual anode was in pretty much pristine condition. And when we did some cross section of it, we see that this is the metal alloy core, and the slag is frozen on the outside. And you can see this oxide layer in between, and that oxide layer is thick enough to protect attack, because remember, oxygen bubbles are forming here at almost 1600 degrees Celsius. And yet they don't fully oxidize the core of the electrode because that electrode is protected by this surface film, which is still thin enough to allow electrons to go across and then react with the oxide ions to form oxygen gas. And so this we published in Nature, and as a result, it gave us some credibility because you know how hard it is to get published in Nature. They publish maybe one paper per decade in the area of extractive metallurgy. This was quite an accomplishment. So we started a company in 2012. I with two of my associates, and we had a different name. We called it Boston Electrometallurgical, which was too complicated for the common person to know. So we changed the name to Boston Metal. And so it's on the path to upscaling the technology. And that involves the design, construction, operation of a self-heating cell. You know, when I showed you the cell in my lab at MIT, it was externally heated. But just as aluminum cells in industry, there's only one current. And that current from the anode to the cathode does two things. It drives the Faradaic reactions, making oxygen on the anode and iron on the cathode. But as the current flows through the molten oxide electrolyte, it generates joule heat. And if the cell is properly configured, that joule heat will be enough to keep the cell at operating temperature. There's no external heaters. And so this is quite an achievement to make this. And then, of course, the other thing we have to master is how to make the inert anode at scale, because the inert anodes that we used for our tests were probably about this big. I'm holding up a pen here. That was adequate for our laboratory test, but you're going to have an anode that's the size of a coffin, and that's going to take some doing with, because as you know, chromium as a massive metal is brittle, so we have to be smart about how we synthesize the alloy at scale. And so success is going to be operation of a multi-anode cell, probably total current about 200,000 amperes, and then we'll be at tonnage iron making. And this is an example of the cell that we designed and built starting back in 2012. This is not quite 1 meter across. You can see there's a human being here. And this is, the cell is open and we're tapping iron. And this is an anode coming in from the top. This was an early experiment, so we were running a carbon anode just to get experience with running the cell, but it's self-heating. You can see the cell. There are no external heaters. The single current from the anode to the cathode pool on the bottom, you can see there's leads going in from the bottom here. That's enough to keep the cell at temperature and to produce iron. So we're tapping iron while passing current. And this is making better metal. It has no carbon, high purity, zero emissions, because the only thing it would be producing once we replace this with the inert anode is oxygen. And our goal is to do this. We've priced it out at their price models, and to make metal at competitive pricing to that of metal today. And this is all unsubsidized. We're not talking about getting government subsidies and things like that. So that's the goal of this. And so I think this would, the integral of all of these characteristics would be characterized as disruption. And this is the face of disruption. This is Amanda. She's one of our steel workers. She's a young woman, and you can see she's really into this. And this is the future of steel making. So now let's talk more about the sustainable model. So we want sustainable electricity all over the world, and then that would give us a sustainable modernity. And so the key enabler, because we know that the sustainable generation of electricity is intermittent with wind and solar. So we need to have stationary storage at massive scale. So what I did when I started the liquid metal battery project is I knew the problem with storage is the price. So I said, well, if price is the problem, then we have to attack price. And so I changed the research paradigm because the way the university operates today, you want to invent the coolest chemistry. You don't care about pricing. Uh, but in this case, I said, no, we have to start thinking about costs on day one, not day 10,001. So that's why I call it cost informed discovery. So it's cost informed at the early discovery stage. So there are vast swaths of the periodic table that I will not allow my people to touch because the elements are just too costly or they're not in high enough abundance. So that was a different approach. So for storage, I said to confine the chemistry to only earth abundant elements. I don't care if I can make a fantastic battery with tellurium. Tellurium is only as earth abundant as gold, so it's not going to scale. So I said in my TED talk, to make something dirt cheap, you should make it out of dirt and preferably local dirt. So that gets you dirt cheap material and locally sourced, so you don't have any problems with your supply chains, and make it easy to manufacture by thinking about the design. And so we were already thinking about a simple liquid metal battery when we started. And the other important thing here is to ask the right question. So you can see here, I'm saying inventing a colossal cheap storage device. I didn't say the word battery. If I say the word battery, then immediately it conjures up an image of a cylinder like a AA battery or something like that. So I said, don't specify the form factor yet. Another thing, I disregarded the experts. I didn't talk to battery experts because they would have all told me that I was crazy, that all this stuff has been tried, doesn't work. So I looked outside the field for inspiration. And so I marveled at the economy of scale of modern electrometallurgy. And here's an aluminum smelter. This is in Quebec. It's in the St. Lawrence River. And this is about, I don't know, 30 meters from left to right. Oh, forgive me, 30 meters from left to right. And it goes back about a kilometer. And that's about 500,000 amperes, 400,000 amperes at about 4 volts. So you can imagine how much, you're talking gigawatts going through there 24/7. So the thing is, you can turn dirt into metal for less than 50 cents a pound. So I said, that's a miracle. And I said, if I could teach this thing how not to consume vast quantities of electricity, but to store vast quantities of electricity and then give them back on demand, I know I'll have something that's big and cheap because I'm already starting with something that traffics in huge amounts of electricity, and I'm trying to teach it how to store. Whereas other people start with a small lithium-ion battery and try to imagine how to scale it up to something of this size. So it's a different approach. So here's the invention. I call it invasive electrochemistry because the only reason I could invent this is because of my history in electrometallurgy. I knew molten salts, I knew liquid metals, I knew how to make aluminum, magnesium, and the people that have been studying lithium-ion batteries and aqueous flow batteries, they don't know this chemistry. They don't have the wherewithal to even imagine this sort of thing. So that's why I'm saying electrometallurgy is crossed with the battery chemistry. So this is the earliest conceptualization of the liquid metal battery with 3 layers, a low density liquid metal on top, that's magnesium, and a high density liquid metal on the bottom, antimony. And there are different parts of the periodic table. Magnesium is a good metal, good electron donor, and antimony is a poor metal. It's a good electron acceptor. And in between, we have a molten salt electrolyte. And the metal is insoluble in the salt, and the salt is insoluble in the metal. And so the 3 layers lie one above the other in order of density. There's no membranes, no separators, and so on. So that was the concept of the liquid metal battery. And on discharge, magnesium wants to alloy with antimony, but I just told you magnesium is insoluble in the electrolyte, so magnesium can't get to the antimony. But if magnesium becomes magnesium ion by getting rid of 2 electrons, magnesium ion can go through the electrolyte. And when it gets to the other side, it acquires 2 electrons. And those electrons that are generated at magnesium and are donated at antimony go through the external circuit. And as they go through the external circuit, they power the devices. And then to charge the battery, we force current through, just as I showed you in the liquid metal battery. We force current from the antimony to the magnesium, and then that causes the magnesium to be refined out of the antimony. So it purifies the antimony, purifies the molten salt electrolyte, and restores the magnesium on top here to its initial pristine condition. And so this was one example, but we had a plurality of candidates for the upper electrode, the negative electrode, some people call it the anode. And so all of these are candidates, and we did work with them. We worked with lithium, we worked with sodium, we're working with calcium right now. And there's a plurality of elements for the positive electrode, for the cathode. So I showed you antimony, but we've worked with lead, we've worked with bismuth. Obviously, we wouldn't work with tellurium because it's only as earth abundant as gold. But if you wanted to be silly, I suppose you could build one like that. So there's a plurality of choices here. And again, a paper in Nature. This was 2015, I believe. And so this again is to show that this work was of high quality. It wasn't just cook and look. So we started a company. I didn't want to start the company, but my students told me that I keep talking about science and services society, so let's go. So we started the Liquid Metal Battery Corporation, which is a terrible name. And then we changed it to Ambry because we learned that Cisco Systems was named because it was started in San Francisco. Well, okay, so we started this in Cambridge. So I played with the word Cambridge and came up with Ambry. And Ambry.com was still available. And our Series A funding came from Bill Gates personally, not from the foundation. It came from him personally. And I met him because he was watching my chemistry lectures online. Why, I don't know, but he started watching them. And at some point, he wanted to come to MIT and visit with me. And so I sat with him and we spoke about computers in education, distance learning. This was 2009, way before Zoom and all this stuff. And towards the end of the meeting, he said, "What are you working on?" And I said, "Well, I had this idea of a liquid metal battery." And he said, "That sounds interesting. Let me know if you decide to spin it out. I'd be willing to put some money into it." So I met Bill Gates not because I wrote an op-ed piece for the Wall Street Journal. I met Bill Gates because of so Bill Gates funded the thing, and Total, the French energy giant. And so now it's 14 years old. As I told you, it's going to take 20 years. Microsoft is first customer in the order book. Xcel Energy is also in the order book. There's a large order book, but they're still on the path to commercialization. They can't release a product until they know that it's going to work. They don't want to release something that's poor quality. So they're expanding their manufacturing facilities. But with LFP crashing the market, coming in, LFP pricing it's below $50 per kilowatt hour. I mean, these are unbelievably low prices. And as we know from the fires that have occurred at Moss Landing, LFP is not the right technology for massive stationary storage, but people are still putting it in because the cost of acquisition is so low. And that maybe at some point the insurance industry will step in and stop insuring these people that are running. So this has caused a lot of stress for Ambry. So I'm going to bring this to a close. There are other things I could talk about, but we don't have the time. There's a aluminium sulfur battery, which was started the Avanti company, and lithium metal battery, which is beyond lithium ion, and that's started the Pure Lithium Corporation. These are other battery chemistries. I keep inventing. When people think lithium ion is the end of the line, they're wrong. There's so much more that can be done that gives us more secure supply chains and so on. So let's go. So last thing I'll say is I started the company Sadoway Labs, which is my skunk works, where I'm working on really wild ideas. I say imagining the unimaginable, and got support from Eric Schmidt, who is the CEO of Google. And with his fund, the Schmidt Futures, I say I imagine the unimaginable and he funds the unfundable. And so we're working on a variety of projects in the area of climate change mitigation. And the thing that unifies my work, as you've seen up until now, it's what I call extreme electrochemistry. So that's all non-aqueous electrochemistry. You see none of my work. I don't touch flow batteries. I don't touch metal air batteries. I think that stuff is so old, I don't touch it. So that means molten salt's going to high temperature, from body temperature up to 2000 Celsius. And we also have some cryogenic work going down to minus 100 Celsius. So I'm going to end by talking about the inventive process. I already told you that we should ask the right question, look outside the field. I didn't hire experts, I hired anti-experts. All of my students and postdocs were new to the high temperature extreme electrochemistry. And I recruit curiosity and perseverance. People have to be hungry to learn, and they have to be stubborn, because this is hard work. There's going to be setbacks. And in my organizations, I don't rule from the top down. I empower everyone. And I encourage independent thought. And here's Niels Bohr with Albert Einstein. Bohr started quantum theory, and Einstein, of course, gave us general relativity. So one was at cosmic dimensions, the other's at subatomic dimensions. And Einstein thought quantum theory was nonsense, and they would argue. And at one point, they got into this argument, and Bohr says to Einstein, he says, "You're not thinking, you're just being logical." And that's the difference between thought and imagination. So use your imagination. And I'll end by reminding everybody that the battery was first discovered by a professor, Alessandro Volta. This is his first battery, a stack of coins, silver and zinc, separated by cardboard soaked in brine. And from this, for the first time, we have electric current. Prior to this, there was no such thing. Electricity was static electricity. This is the first time we had electric current. And so Volta gave us not only the battery, he gave us the modern age, because this entire conversation is brought to us by electric current, electrons in motion. And that's what Volta did. Volta is underappreciated for how he changed the world. People talk about Tesla. Tesla was brilliant, no question, with the AC and on and on and on. But Tesla would not exist were it not for Volta. So please remember that. All right, so pretty much all industrial chemistry will become industrial electrochemistry. Thermal chemistry, no more gas. It's going to be electric heating. So it's a bright future in electrochemistry. And it's a bright future in electrometallurgy. You see, everything is electro something. So anyways, I think I hope I've shown you that there's a way to cross product between science and service to society and profitable sustainability.